Okay, we are going to start with exponential functions now, lesson 7.5. This lesson kind of took a long time in class, so I've already got a lot of it written out. You're just going to kind of have to follow along. You're going to have to pause it as you go and make sure you get things written out, because I don't want to make this video too long. I want you guys to watch it from beginning to end. In class, we watched a video. It was called Folding Paper to Get to the Moon. If you want to just YouTube it, you sure could. It's actually a really interesting video, and it basically proves that you can fold a piece of paper 45 times and it will touch the moon if you can do that. Now, obviously, you've heard that if you fold a piece of paper in half, you can only do it 7 times. But like, even if you were to cut the paper in half and stack it, 45 times would get you all the way to the moon, which is really, really, really incredible. So just something to kind of think about with that. But that's how fast exponential functions grow. And exponential functions, that's what we're talking about in this lesson here. They start to pick up really fast and grow really fast, as you'll be able to see as we go through some of these questions. So let's get started here. It says, does the table represent a linear or an exponential function? The one way to figure that out is to see if they're being multiplied or added. So from right here to here, it looks like we're adding 2. Are we adding 2 to get to that one? No, we're not. Or I guess that would be subtracting 2. But it's either way, it's not subtracting 2 on either of those. What's happening here is we're actually multiplying by a 3. And we're multiplying by a 3, and we're multiplying by a 3 again. So we are multiplying by the same thing every time. It's just a 3. So that one would be exponential. Next one. We have same type of thing going on here, except now we're adding. We're actually adding 2 every single time. So if I'm adding 2 every single time, that's a that's linear. That's a linear function. So that's how you tell the difference. One of them is multiplying and one of them is adding. Okay, let's get into some graphing here. This is what an exponential function looks like. You always have, I'm trying to get it in frame here. You always have an exponent for your x, or sorry, your variable is always an exponent. And we're just going to plug things in. So I'm going to plug in a -3 for that x. Actually, no, let's start with 0, because 0 is easy. 2 to the 0 power is 1. 2 to the first power is 2. 2 to the second power is 4. 2 to the third power is 8. Now we can see what's happening here. These are doubling as we go down. So we're going to go the opposite way to get back to -1. So if I go backwards, we are dividing by 2 there. So that would be like a 1/2. This would be like a 1/4. And this would be a 1/8. Okay, so now I'm going to graph those up. So finding 0, 1, that's right there. 1, 2 would be right there. 2, 4 is right there. 3, 8 is right there. Going backwards, 1/2, 1/4, 1/8. You can see what's happening there. And now the question that I would ask you is, does this trend ever look like it's going to go down like that? And to some of you, you might say yes, but it's important that you know that it actually won't ever cross that line, because I could keep cutting it in half as much as I wanted. I'm going to get a 16th, then a 32nd, then a 64th. It's going to get to be a really small number, but you got to know that that's actually not going to go below 0 or even touch 0, because we could cut things in half as much as we want, but we can't get to 0 by cutting something in half. Even 1,000,000 times, if you cut it in half, you've still got something left. It's just a really small number. So that's one of the most important things to know from this unit here. As I draw my line the best I can here, I got to remember that I will never ever cross or touch that 0. So that's what my line will look like. Now this line looks like it's about to go straight up, and it will go up really, really high, but it should always... It's always going to be going to the right as well. It's always going to be going this way and up. So that's a couple things we need to remember as we get into our next thing here, which is domain and range. Domain is basically asking us, what x values could we possibly put in for x? Well, you can put whatever you want in for that x, whether it's a positive number, a negative number, a fraction, it doesn't matter. So domain, when we're talking about graphs, like this one that we just graphed, when we talk about domain, it's going to be any number that you want it to be. So we call it all real numbers. All real numbers. Our range is a little bit different though, because we know that this line will never touch or cross 0 or be on this side of the line. It's going to get really close to 0, but it's not ever going to cross it. So our range is going to be all of our y values have to be greater than 0. And they can't touch 0, so I can't put an equal sign either. You can cut things in half as much as you want, but they will always be greater than 0. Next one. As you can see, I already plugged these numbers in, I already got numbers out, and I already have it graphed. So 1/2 to the x power would look like this. Oh, I think I did it backwards. Well, you get to see me graph it, because I did this wrong. I was not paying attention apparently when I graphed it. So at -3, it needs to be at 8. So that's right there. Okay. At -2, it's at 4. You can graph this with me now. -1, we're at 2, 0, 1, 1 1/2, 1/4, 1/8, and 1/16, and so on. You could keep going. But my graph actually looks the opposite way that I had it drawn out before. Again, so now my question is for my domain. What could have I put in for that exponent? I could put whatever I want. I just randomly chose these numbers, -3 through 3. I could have done -87. I could have done +74. It doesn't matter. There's no restrictions on my x's. And I know that it will always go that way and that way on my graph too, because this line will continue to go up and over to that direction as I go. So my domain, again, is all real numbers, which you could just memorize. It's always going to be all real numbers when you are graphing something. My range, though, again, I'm not going below that line. I can get really, really close to 0, 1/2, 1/4, 1/8, 1/16, 1/32, and so on, but I will never cross it. So y always has to be greater than 0 again. Here's my general form equation for exponential functions, a times b to the x power. That's what all of these looked like up here. So we had a y equals basically, f of x is the same as y, and then something to the power of x. Now, to get more specific with it, a is actually going to be always your starting value. So where are you starting? B is going to be your rate of change, basically. So I'm actually going to write that out. I would like you guys to write it out too. Starting value, or you could put initial value. B is going to be my ratio. So how is that changing? If it's doubling, that's where that would go. If it's tripling, you'd put a 3 there. If it's quadrupling, you put a 4 there. If it's getting cut in half every time, it'd be a 1/2 in that. So that's your ratio. So as you can see up here, if I highlight them, this 2 means we were doubling. So they were going up like that. This 1/2, that's our ratio. That means we were cutting in half every time. You can see that that's going down. This is called exponential growth right here, because you're growing as you go from left to right. And this is called exponential decay because you're going down when you go left to right. We'll get into more of that in the next little episode here, though. Is the function linear or exponential? Well, I know this one is linear because that's in the form y equals mx plus b, and there's no exponent. So that's linear. This one is exponential. And I know that because we have a variable as an exponent. That's the one thing you have to look for. Okay, I've already got the next two almost finished up for us. It says how many bacteria will be in a culture or whatever if there are 2,200 at the start, and here's our function. And then it says how many will there be after 5 hours. Well, that 5 is going to go in right there for that x, because that would be like your input, and x is usually time in these types of questions. So that's what I did. I plugged it in for that x. I typed it into my calculator, and I got 70,400, and I should write bacteria on there for a label. It then says, what's your domain? Well, in a word problem, domain is different because up here I told you guys domain is always going to be all real numbers. Well, that's only true if it's a graph that you're graphing. In a word problem, it's a little bit different. In a word problem, our domain is time. It's like almost always time, and time has to have a starting point because we can't go back in time until time machines are invented. So let's just say time starts at 0, because that would be when our time actually starts. We're looking to see how many bacteria will be there after 5 hours, but time has to start somewhere. So we're going to say our x has to be greater than or equal to 0 because our time starts exactly at 0, so I can have an equal sign there. The next question is my output, my range, because domain is like your x values, range is like your y values. Y values are your outputs. This was my output in bacteria, so I actually have to figure out if my number of bacteria is going to be a minimum or a maximum. 2200 was the minimum bacteria that I'll have, and it'll keep growing. So my range here is going to be y is greater than or equal to 2200, because that is the minimum number of bacteria that was possible, basically. So we've got 2200 bacteria at starting time 0, but then it just grows and grows and grows. So y has to be greater than or equal to that 2200. Next, same type of situation here. This was our equation. Oops. This was our equation there. And it says 56 days. But it wants our beetle population to double each week. So I converted 56 days to 8 weeks, and I'm going to use that 8 instead when I fill out my equation here. So I use that 8, as you can see right there. I did 30 times 2 to the 8th power, and I got 7,680 beetles. Now it wants a domain and range. My domain, again, is going to be, if we're talking about time, which we are, our domain, our x values, is going to be greater than or equal to 0 because we have to have a starting point at 0. And our range is basically how many beetles we had at that start time. So our y, our number of beetles, was 30. It says suppose 30 flower beetles were left undisturbed. So we had 30 at the start, and we know it's growing, so y is going to have to be greater than or equal to 30. Last little question here. I already know right off the bat, well, it says what is the graph of this, so you can obviously see that I've already graphed it. But my domain is going to be all real numbers because it's a graph, and that's what we've been talking about. Our range, it looks like we're not crossing 0 again, so y is going to have to be greater than, oops, I put equal to. Our y is going to have to be greater than 0. Same situation right here. All real numbers. Our range, y is greater than or equal to 0. And you guys can check out that graph too. Domain and range, as you can see, x is going to be all real numbers. Our range on this one is going to be y is actually greater than this -3. So they actually moved it down just to kind of show us that you can do it at different levels too. Our y is greater than -3 there. And on this one, our y is actually going to be less than because the line's below that -1. But you'll see those on Alex. I just got to get this video wrapped up. Thanks for watching.